We better start. Good afternoon and welcome to the 6th webinar in the NIWA and SPC Learning Exchange webinar series. Many thanks for your feedback and for the interest you show in the initiative. A special welcome to the colleagues from the New Zealand Crown Research Institute GNS Science for expressing their interest in joining the webinars. Here they joined the group of organizations including NIWA, SPC, SPREP, MFAT, DFAT, and Geoscience Australia. It is good to see that the number of organizations is growing. That tells us that the learning that we share here is of value to the region. Before we start, few housekeeping matters. The webinar will last for about 60 minutes, 45 for the presentations and 10 to 15 for questions and answers. Please hold your questions until the questions and answers time after the presentation. However, you're welcome to ask your question in chat box at any time. The event is recorded and the recording will be published on the SPC YouTube channel, and the link to the recording will be made available on the SPC website. Please let me know if you object to that. Please mute your microphone and close your camera to minimize bandwidth needs. Today we have presenters from NIWA, Dr. Christian Zamit, hydrologist, and Dr. Celine Gilbert, hydrological forecasting scientist. Their presentations will briefly describe the water model, New Zealand water model, modeling framework that aims to generate accurate river flows simulations for nearly 40 million of river reaches in New Zealand using an ensemble of hydrological models. Then they will touch upon river flow forecast research project that can produce hourly forecast for the next 48 hours. It would be interesting to learn how replicable these models are and whether they can be used for forecasting river flows in other countries in the region. I'm looking forward to hear more from the presenters, and I hand over to Christian and Celine now. Christian and Celine, you're welcome to start sharing your screen now. Thank you.
Hi, can you hear me? I believe Christian will be starting the seminar.
Sure.
Can you hear me?
Please. Yes, we can hear you. Christian, please go ahead.
All right. Good afternoon. I hope, I hope everyone can see the PowerPoint.
We can see the PowerPoint and we can hear you clearly. Please go ahead.
Okay. Good afternoon. Thank you for the invitation and thank you for turning it. I will briefly describe the New Zealand water model and one application of the New Zealand water model to climate change impact and assessment. The New Zealand water model is a collaboration between 3 CRI in New Zealand, GNS Science, Manaki Whenua, Landcare Research, and NIWA. With participation and collaboration from regional council and central government. So what is the current challenge that we have in New Zealand? We need reliable river flow and groundwater level information across spatial and temporal scale for a multitude of freshwater management activity, going from planning and policy development to climate change impact assessment to environmental flow setting, so on and so forth. And this is quite significant as a challenge in New Zealand due to the complex interaction that we have between land, vegetation, climate, and the hydrological process associated with it. And we have a relatively sparse network of observation. As a result, if we want to be able to look at what's happening not only in the past, what happened in the past, but what's happening in the future, we can't go and instrument any river or any piece of groundwater in New Zealand. So we have to rely on models. And those models can be purposely built for one location. But generally, if we want to be able to produce such level of information across New Zealand. We need to have models which are flexible enough to represent a wide range of environmental conditions and complex enough to represent the integration of natural and anthropogenic process in order that we can disentangle both and looking at combination of both in the past and the future. So what is NZWaM, or the New Zealand Water Model? It's a versatile hydrological modeling framework that aims to couple both land surface and underground processes at a specific scale and above. The aim is to be able to produce not only river flow, but hydrological flux and groundwater level from catchment scale to national scale across different time scale, with a specific focus on being able to predict our climate, land use, and water use, and potentially other environmental stressors impact water resource availability and weather-related impacts. And we aim to have this modeling framework being used for a wide range of application, going from integrated resource management, infrastructure planning, water accounting, water allocation, climate change impact assessment, and subsequent adaptation strategy, environmental flow setting, hydrological flow drought forecasting, and a large number of science investigation and potentially everything that you can think about. It's not the model that it will do everything and anything, or it's not a modeling framework that will do everything and anything, but it will do we aim to have something that is doing a large number of those things. So how do we do this? We basically link, and there is nothing new under the sun, we basically link environmental data of different source, different sort, with different submodel that represent different hydrological processes that could potentially be extended to ecological or water quality processes. And we do this currently on the cloud-based modeling framework, but we are currently working with NESI to see how this can be moved on the high-performance computing in order to be able to leverage the computing power of that is offered to us. And this framework is aimed to be dynamic in order that accuracy of the river flow and the hydrological processes, not only in terms of timing, volume, but regime, to increase with time, which make this modeling framework much more realistic, or let's say much more usable across a number of different use for different users across different thematic of research. Because we are looking at something that can be run at catchment, sub-regional, regional, or national scale, we are relying on developing uncalibrated hydrological model everywhere that will be a priori parameterized, but that can be tailored to specific condition or specific setting if need to be. Obviously, those uncalibrated models are going to be benchmarked or calibrated or verified, if you want, based on the network of observation that is available every year to us. So how does it look like? The New Zealand Water Model has 5 different modules. You have a surface water module, which is coupled or uncoupled to a groundwater module, which is coupled or uncoupled to a water edge. And those 3 modules can be talking to each other or not. All the hydro-geological and spatial information is provided through what we call the hydro-geofabric. That is feeding both of those 3 different modules that contain model parameterization, model description, and regionalization procedure. And each of the components of the model can be validated or benchmarked against observation, either in a decouple or couple mode. And everything then after is delivered through a tool which is called hydro-desk NZ. That is basically a way for us to deliver all the science that we are doing in the background to the end user. So how hydro-desk is working, it's a cloud-based system that enables you to run for everywhere in New Zealand the different model and the different coupling which are open offered to everyone. So currently it's we can run the model for 576,000 reach in New Zealand. Celine will talk about an application at which is looking at 43,000 reach. Or no, sorry, 63,000 reach. The latest version that we are currently developing will be able to work at over 4 million of location in New Zealand. And how it's working is simply you register your interest, you get a password, and you can access everything. All just in a new science development as an end user without having to bother updating your system, upgrading your security, updating the information, so on and so forth. Everything is done for you. You just select where you want to do the model, you select the model, you give the parameter, you push a button, and you get output in a nutshell. So I would like now to talk a little bit about climate change application, which is something where we have done quite a bit of work in association with the different national science challenge, especially the Deep South challenge. So how do we do this? The NIWA climate team is taking the information from IPCC, put it through a regional climate model to provide regional climate projection. We couple those hydrological projections, the climate projection with the hydrological model, look at hydrological impact, which are then associated with environmental impact. So that's basically the modeling chain that we are using. I need to use that one, sorry. In the case that we currently have only one regional climate model, which is run by NIWA, with 4 RCP and 6 GCM, which are being described for New Zealand purpose. We have 2 versions of the hydrological model, and we're running this at a scale of 7 square kilometers across the country. That gives us around 2 petabytes of information that we will not be able to have access to it, or to access to, if we were not beneficiating the use of the supercomputer. So not only does supercomputer give us a large storage where we can really tease out a number of things, but at the same time, it enables us to do some science that we would not be able to do without such a performing tool. The river flow simulation that we have are validated under climate change. So you can't do the typical validation that you are doing under typically for hydrological model, but you can validate against hydrological characteristics, which is a publication that has been done by an ex-colleague of mine named Daniel Collins. So one of the things that those modeling ensemble give us access to is be able to tease out uncertainties under climate change. So on the top of the figure here, you will have all the model put together for one climate variable. Let's say that's a change in mean flow in New Zealand, represented for the 63,000 reach that Celine will be describing a bit later. So everything which is in blue, you have an increase compared to the past. Everything which is in yellow, it's really remaining the same. And everything which is orange to red as it corresponds to a decrease. So if you were looking just at the top of the figure, you might say, well, there is plenty of things which is happening in quite a large portion of the country. But because we have those different modeling ensemble results, we're able to tease out and we're able to describe some level of certainty associated with those models. And once you take this into account, and you, for example, you are looking at a 95% certainty or confidence level, you can see that there is a lot of things that appeared into the modeling output that suddenly disappeared. So, sorry, those tools associated with the power of the HPC give us the ability to really develop some decision-making threshold that can inform policy or location where policy is going to be applied. The other thing that we can look at, because we have such access to such a large amount of data, is when events such as flooding, for example, are happening at the same place at the same time. So here on the graph, you have on the vertical axis for different level, different region of New Zealand, for different time slice, the change in the one-day flooding, concurrent flooding happening in New Zealand. So it's all happening, every bar is happening at the same time. And you have a change between 0% and 100% of the region being flooded at the same time for different RCP under a certain level of confidence. And what you are saying with this is that during severe storm, more and more river will be in flood at the same time, which is an indication that it will put some pressure on emergency response that is likely not to be localized, but at a much more wider scale. You start to see some compelling signal that start to emerge around mid-century about quite a large number of regions being flooded at the same time. And you can go and delve into some regional analysis if you want. Another aspect that we have been looking at is because New Zealand has quite a large agricultural based economy, we look at the potential impact of irrigation supply, demand, and reliability across New Zealand. So all the land that you are seeing either in color or in shaded area correspond to land which is currently under agricultural land that can be irrigated. So it removes all the agricultural land where the slope is larger than 7%, for example. So how do we look at the supply? We look at a multi-modal median change in the mean irrigation season flow, and we look at the change between two scenarios here, an ensemble of scenarios for RCP 2.6 and RCP 2.5. This gives us a picture that is showing that in terms of the change in the supply, you are not going to see a lot of change, assuming that you have a 95% level of certainty across New Zealand between now and mid-century across the different RCPs. If you look at the same thing, looking at the plant water demand, you can see that under RCP 2.6, you have access to some information that tell you, well, there is not a lot which is happening. However, a lot of things are happening under RCP 8.5. You have a lot of change in irrigation demand, which is resulting for a combination of change in precipitation and temperature. Those changes are in percentage. So that's one bemol that might be taken, or one caution that might be taken with this type of information. There are such change into percentage. So it's not a change in volume. If you were to do the same calculation in terms of change of amount of water, you will see that this area, which is a Canterbury area, which is the largest irrigated area in New Zealand, is the one which is having the largest change, whereas all the red that you are seeing here are becoming far less prominent. Once you combine the supply and the demand together, you can look at the reliability of supply. And this is based on the national scale assessment. So we use a national scale assessment, which is called National Environmental, I can't remember the name, sorry about this. And what we tend to see is you can see those different areas where we start to see some significant decrease in terms of reliability of supply happening throughout the year. Obviously, you can go further into the analysis, and we've done quite a bit of work on this, but just to give you a taste of the type of information that you can get outside of those models and looking at a large-scale assessment that can be carried out. And you can even go to the point where you can start to look at the time of emergence. So the time where the climate change signal is starting to be prominent compared to climate variability. So here we're looking at the time of emergence for when we look at a multimodal medial change for irrigation water demand. And what we are seeing is across the different RCPs, we are seeing that the North Island of New Zealand is going to be much more sensitive to climate change than the South Island. And the signal in terms of irrigation demand is going to come much more earlier than in the southern part of the country. In terms of future work on the New Zealand water model is to do a full coupling of the surface water and the groundwater component with a demand model. So far, you can run the surface water, one surface water model. You can run one groundwater model. We are in the process of putting together a couple surface water groundwater model and an additional groundwater model. So you will have all those different model combinations that you can play together to better describe your uncertainty. We will be able to link with a water edge to provide water edge distribution and link to quantity and quality. For climate change, is using the same modeling chain under IPCC 6, develop hydrological and climate bias correction, as well as regional scale integrated assessment. Thank you very much. I think I'm just on time.
Thank you very much, Christian. The next presenter is welcome to start sharing her screen. Celine.
Hi everyone, showing my screen now.
Excellent, we can see your screen and we can hear you clearly. Thank you very much. Please go ahead.
Excellent. Thank you for the opportunity to share the work that I've been involved in at NIWA. So as described before, this is about describing a research project that we've been doing to develop a flow forecasting prototype. And so the key aim of the project is to study the scientific feasibility of the system and to explain the challenges that we've faced and the decisions that we've made to basically build the model and evaluate it. And then I'll just touch base on the perspective and what we've learned from doing all of this. Quickly, I've put a link into the chat where you can click on the video that shows a current output of the flow So this was for the Canterbury flood event. I'm also sharing this with my screen, but with the delay, I'm not sure, you know, how good or smooth the video is. But feel free to click on the link in the chat. So this just shows basically what the flow forecasting does, which is produce 48-hour hourly flow forecast in a relative sense across the country in New Zealand. So here we go. So there's quite a lot of people involved in the project. It's quite an interdisciplinary team. And although there's quite a lot of us involved, we're not full-time on the project. So it's certainly a project on a budget. But we've done an amazing job at talking to lots of other people and components to get to where we are. And there's definitely a lot more work to do on the project. I'll briefly touch base on what's being done overseas and why we now have this trend of national global scale flow forecasting. I'll talk about the hydro-meteorological and flood context in New Zealand. I'll go over the prototype, the consultation process, the model and the implementation. I'll talk about the forecast communication, which is quite an important aspect of the project. And we'll finish with the evaluation. It's still ongoing, but I'll show what we've got so far, and discuss a little bit some of the challenges and perspective. So overseas, there's quite, in the last 15, 20 years, there's been a lot of development in Europe, in the US as well, in the world as well, with those big models covering entire continent or even the world to develop river forecasts. So often they only focus on larger rivers, but really the driver of the ability to do those systems resides in the fact that there's new weather ensemble forecast available, and it's better than ever. And there's large special data sets that are available, and a lot of improved computing and enough power to run all those models. So these, you know, and there's a bit of an economy of scale in looking at a national scale or global scale view of what is going on in terms of river and river flooding. So within the context of New Zealand, sorry, flooding is the number one, it's the number one costly natural disaster in New Zealand. You can see some cost of insurance costs between 1996 and 2014, which are very similar to only less than 2 years from 2017 and 19, where we had about 6 egg cyclones. New Zealand is very particular, where there's a lot of rivers. The orography is very challenging. You go from the sea to 3,000 meters in less than 40 kilometers, especially in the South Island there. So lots of very steep rivers, short, fast responding. We also have a lot of rain, especially on the west coast here in the Southern Alps. You can get a lot of flooding coming from atmospheric rivers as well. And so the amount of water that can go into the river in New Zealand can be quite significant on the international stage for the size of the rivers that we have. The other important component is the responsibilities for floods in New Zealand. It's all very much to local authorities who are the primary agents that are responsible for civil defense and emergency management. And you can see that the population in the south is much less than in the North Island and in centers like Auckland and Wellington. And unfortunately, the forecasting capabilities can be commensurate with the population in the event of funding kind of available. And so hence the ability to have a bit of a national view to help the local existing models responsible for flooding is kind of one of the key driver behind the project and the feasibility study of this. So the next slide is giving an overview of the system. So there's quite a lot there, but really there's only 4 key components. So the first one, you need meteorological forcing to go into your system. Then you're producing some hydrological forecasts. you need to do something to the output with some post-processing, and I'll explain a bit more what it is, and then you need a way to communicate that information. And so the entire system is built basically on those 4 key components. Underpinning the meteorological forcing, it's NIWA's high-resolution convective scale model, NZWaM, which you can see it's coming from the unified model, and it's the version for New Zealand. Underpinning the hydrology is NZWaM, which Christian described earlier, so I don't need to explain anything there. But a key aspect is that we need 2 sets of inputs here in blue. We need some initial conditions to fit into each forecast. Every time we update a forecast, we need some to know what are the conditions to start the forecast from. And we need a lot of data, the river, the network, all the geofabric data set that Christian kind of mentioned as well. So one of the key components as well in our system is that we have a deterministic weather forecast. So we only run one high resolution weather model, but we produce an ensemble of forecasts. And the way we do this is by perturbing the precipitation and perturbing some of the states of our hydrological model to try to have a better bound on uncertainty. And so what we get is an ensemble flow forecast. So we get not just one answer of what the river flow discharge is going to be, but a little bit of a bound of error, which may be, you know, enough or too narrow. But the next step is that we need to produce a reference flow climatology. In our case, we went for a relative sense of expressing the forecast, and I'll explain a bit more why. So to express that reference, whether it's above or below normal, you need a reference. So we need to run simulation on the supercomputer of the model for a very long time. The next step is then we can produce those categories with that reference, and then we can produce the visualization. So why national scale? So we had a big engagement process as part of the project, and the key message that we got from this was that we wanted to have a co-design approach to really complement what existing local models are doing. So existing local models are calibrating models with local data, and so they're definitely going to do much better than a national scale uncalibrated model. So the idea here wasn't to replace what they already have, but more to give a broad, coarser view that's complementing what they may already have or may not have. Often local regions don't have models across all their rivers, so the national scale kind of can bring some information where there isn't a gauge or there isn't any model already in place. So that's the idea there. But the key thing from the process is that it took quite a few years and different formats of presentations, workshops, questionnaires, interviews, and each of those engagements kind of gave us a bit more refinement of our priorities of what we should focus on in the development, or what is important to key stakeholders. And also it raised some of the issues of, okay, for example, getting their data into the system as soon as it's happening is quite, you know, critical from their perspective, but it's not something that unfortunately we can do because there are some data challenges, like there's an embargo, we can't have access to the very latest data. So those are obviously barriers that have been raised through the engagement process that we need to get over at some point to kind of pursue the development. Another issue that we've faced is the data. So NIWA has some rainfall data, and there's many other sites but available via other organizations. As I was mentioning before, there's an embargo where we can only have access to data from other organizations after 24 hours, so it's not quite in real time, so there's a bit of a delay. The other thing is that we do not have a national flow database in New Zealand. Each regions may have their sites, and so the process of gathering data across the country is very manual, and it's not in real time. So you'll often have a delay on when you have the data, so maybe 6 months later across many sites. And so this is quite challenging for us to have a model and not being able to necessarily test in real time everywhere, or even use the information to improve the model. The second aspect is, as Christian mentioned, the model is modeling information, so what the river is doing across about 50 or so thousand basins. So you can see here a close-up. And so it's so much more information available than we can actually check. We can only check at a few sites. There can be a lot more sites, but we've, for the evaluation, we've kind of decreased our site numbers to make sure that we had, because some sites the data wasn't quite long enough or wasn't quite clean enough for checking all flow kind of regime. So why we went for a relative sense is because we wanted to go national scale where there isn't data. So it's trying to focus to the ungauged sites, and so we can only give that information in a relative sense. So it might give you a better idea of whether this is really high or very low. And so the way we did it is by running the model for a very long term across all the little basins that you've seen in the previous slide, and then derive what we call a flow duration curve, which is basically sorting all the flows in there. From the high flows are the flows that don't happen very often. And so this is what we've categorized as extremely high. So that was our threshold. And then the flows that are kind of happening in the mid-range, might be our normal kind of threshold, and so on. So this is how we are communicating the simulations we're getting from the forecast. This is an example of an event in March 2019. So this is the raw forecast and calibrated in blue. The red was what was observed. You can see that it struggled early on to kind of picking up. The deterministic was way off, but within the ensemble, it was roughly in the range. When you look into categories, this is what you're getting here, looking at from a category. So you can see that it was roughly in the extremely high category during the top of the event here, for example. So one of the key things to run the project is that the weather forecast suite is using Silk, which is an automated system running on our supercomputer that automates everything from getting the data, running the system, processing the data, and repeat every day, several times a day. And we've had to develop a similar automated system for the national river flow forecast as well. We've parallelized across the region. So this is the yellows here, so it runs a little bit faster. One of the key issues, again, from the data not getting there on time means that our initial observations have about 2 or 3 days delay. So we have to bridge between the observation we have with, older forecasts up till now, so that we're ready to run for the next forecast. So this is quite a challenge that we need to, next improvement would be to try to bring those initial conditions a bit faster into the system. In terms of the visualization, it's a lot of data, and visualizing it in a meaningful way has been quite a challenge as well. What was the fastest was actually developing videos, which NZWaM has been working on a few years ago. And so this is where the videos came about. And that was basically our first way to see what the model was doing at national scale with a national view. And because it's relative, we had to make bigger rivers thicker, otherwise you lose that sense of which rivers have bigger flow in terms, because everything is relative. Another key thing is that we are now testing having some of those videos being public and available via doc, and we're very keen on any feedback, and often they are disseminated via social media. We've also been working on a website. Again, it's to see what's going on with the model, to understand where things are working, where they aren't. It was very challenging because it's a massive amount of information, but the website approach allows us to also look at the hydrograph, which is a step further from the videos, and also look at the ensembles. In terms of the evaluation aspect, so we have the flow climatology from 1975 to 2020. So we've got about 300 sites that we've set on, and that we can look at how they're performing in terms of a relative sense. So we have done that work as well in terms of an absolute sense, so directly the simulation versus observations. And often, so the results are quite similar with the categories. But if you look at the question of, what was the accuracy of the model in predicting the correct category? So here there's 6 categories relative to that of random chance. You can use a Gerity score. So it goes between -1 and 1. 0 is no skill. So here everything is above 0, which is good. So it's got more skill. When you look at the absolute flow, often some sites don't have skill, but when you go into a categorical version, a lot of those bad sites are actually performing quite well in a categorical sense. So the key thing is the North Island is doing quite well, and the west part here. The areas where the model isn't performing so well is in the middle here. It's got a lot of volcanic kind of geology around here, and then also in the south in the drier part here, drier, colder part. And you can do lots of things to understand, why in the categorical sense it might be performing worse. So for example, this is just showing here the worst performance. This is when you look at so if you look at the time series of your discharge, some will have a very low coefficient of variation, so they don't change much or very smooth. Some will be changing a lot, so the signal, from floods will be quite different. And so in a categorical sense, when you have a low coefficient of variation, your model tends to underpredict the base flow there, and the model tends to have a flow duration curve that's too steep. And that means this is where some of the categories are the worst. And so those low ones are right here around this area, which kind of shows the worst places where it's performing, and also here. If we look in terms of, oops, sorry. Oh, here we go. I'll skip this, but may come back full time. So if we look at the flood aspect now, we can look at, its hits, misses, and false alarm. And so the CSI is the critical success index score. And this is for the top category, so 99% threshold. It usually corresponds to a 2-year flood event, roughly. And so you can see here, obviously, the scores are still better than 0, so it's still better than no skill, but you have shifted down a bit, so the performance is worse than, in a categorical sense. But also what's interesting that you didn't have for the categories is that the lower catchments are doing much worse here. And you can look at what else. So if you look at dry catchments and really wet catchments, you can see that extremely wet catchment do underpredict the base flow. So the water, when it rains, will go more into the river rather than the base flow, and you can see that the number of peaks is too high from the model here, and that also corresponds to too many false alarms for the very extremely wet catchments, and that corresponds to the worst cause for detecting that flood event. So the CSI, it penalizes if you miss, and it penalizes if you have false alert as well. So it's quite a tough score. So by doing all of this, we can try to understand, okay, the model needs some improvement in the pathways of, going base flow, quick flow. And then we understand where the model is doing well or not. So in terms of the forecast, we have a shorter period that we can look at to evaluate. So we've done a reforecast of 2.5 years. We had a preliminary report on about 40 sites, and now we increasing that to the 300 site or so, but we haven't quite finished there. But the current results are showing similar to the 40 sites. But basically, the ensemble approach is improving the performance. And one thing that we do have is we have a little bit of a wet bias. So our weather forecast, which is at a higher resolution than our climatology, is a little bit too wet. And you can see this in the forecast where the the bias is kind of increasing as you go further out into the forecast. Canterbury flooding event, from a qualitative aspect, the forecast was kind of showing the most affected rivers. The pattern was about right. We need to go into more the quantitative aspect to have a better understanding of the performance there. So that's one of our next steps. We're waiting to get the data there. But the idea of the advantage of this model is that you may not get the absolute values of how bad the flood is, but it does give you a picture of what part of the country may be affected and which ones might be worse. So I think that's quite the key message from the research project there. So key challenges, getting real-time data access is problematic to improve the system, but also for validation and verification. The engagement with stakeholders was quite key in the co-design aspect, and also kind of helping us prioritize what we needed to do in terms of the science and what was important to end users. The relative forecast information. So obviously we want to go beyond this, and the next step might be to look at machine learning. We've done some projects there, and there's a lot more work to do there. But the point is that it does bring you more information than just rainfall, because it might tell you which river might be worse in a spatial sense. There's some further development to do with the model to better understand the flood process, and especially differentiate between the quick flows and the slow flows. And one key aspect of the project was connection as well to the international community, to kind of gain a bit more perspective from what is being done overseas and how that may or may not apply to our context. Our context is that we've got short rivers, we've got high resolution weather forecast. Other models overseas are looking more at a longer term and kind of a larger type of catchments. So this is kind of the unique aspect of New Zealand. But the key point is that the scientific feasibility of the project as a proof of concept, I think, has been kind of established. But obviously there's a lot more work to go beyond a relative sense, and this central to all this project was also being able to roll all those models data on a supercomputer as well. So I think I'll stop there. Thank you.
Many thanks to the presenters. We now go to the questions and answers section or part. And we do have a couple of questions that are in the chat box. Let me get to the chat box to start with. Something's wrong with my chat box. Where is the chat box? Okay, so many thanks, Christian and Celine. The question is from Doug. Assuming the meteorological or climate projection input conditions are available, how much effort would it take to establish the water modeling framework elsewhere, for example, on one of the larger Pacific islands, such as Fiji or Samoa?
So my answer was really, it's really depending of the models that you are choosing, the data set that you have to build the hydro-geofabric, because without this, you can't really do anything. Then after, once you have the hydro-geofabric, I will not say it's relatively simple, but it's a simpler process to be able to build those type of tool, especially the web-based version. But there is a certain number of conditions that are essential for us to be able to do it.
I would just add to that it's also quite essential to start even before you have everything in place, because it's a bit of a chicken and egg. When you start one aspect, you will notice that your data, soil data, is not quite good enough, and then you might improve this, and then you realize that your river network information is not quite good enough. And so starting that I guess, national scale modeling isn't too early to do, even though you may not have all the data available.
Yes, I totally agree. We are at the third version of the digital river network. We have 5 different versions of the land cover, 2 different versions of the soil information. It takes time to build all this information together, and to then after put it into the model. But with the framework as it has been developed, you can, in a simple manner, you can do some intercomparison between the different components of it and see where you might have to do some more work. Because as a hydrologist, data is never good enough.
Thank you very much, presenters. If I may ask, where is information on hydrogeofabric coming from? I'm assuming that's information on river network and the size of basins and the amount of water that flows through the basins during the certain periods. Is that correct?
It's part of it, yes. So all the information is based on the national scale information that are available through the different CRI or through New Zealand Land and Resource Inventory. The digital river network is something that is based on a DEM that is hydrologically connected. So the methodology to derive such information has been well established and well publicized everywhere. It just coupling up the information together. We haven't have a full detailed web page that we can refer to, but there is a number of publications that we can give you access to that describe how the data was put together from which source at the time.
The reason I'm asking is because, and of course, I'm not an expert in the field, in that particular field. SPC is working on Digital Earth Pacific, which will work with satellite information that in certain areas of the world was able to collect information related to flooding and was able to measure coverage of water-based areas and so on. And I wonder, has anyone ever thought of using satellite information to establish hydrogeofabric information base for this?
Well, I know that a similar concept has been developed in the US as part of one of their 3 national water model based on SRTM information. So yes, it's possible. It's as long as you get a consistent set of national scale information, either land cover or elevation, that will give you one version. There is nothing that stops you to then after go and improve this information. So for example, we started this process 10 years ago using a 30-meter resolution DEM that I believe was based on SRTM at the time. Now the latest version is a process satellite-based information at 8 meters, which has been merged with LiDAR information. And the next version will use LiDAR information wherever it's made available to us.
Thank you. We have another 2 questions that just arrived. The first one is, thanks for the presentation, Celine. Just to understand, what are the NZWaM and NZCCM as meteorological forcing? And Celine, can you please start by explaining the acronyms? Thank you.
Yes, so NIWA uses the unified model for the weather forecast, and so it's based on the UK Met Office. So we get the global version, so it's quite coarse, it's 17 kilometer squares or so. And I think Stuart is probably answering the question there. But basically, then we develop a regional version of the UM. So we go higher resolution, but just on our grid over New Zealand. And so that's NZWaM. So it's a New Zealand limited area model, and this is at about 4.4 kilometers. So we're basically increasing in resolution for our own local purposes. And then we go beyond the 4.4 kilometer and we use NZCSM, which is the convective scale version of the model, and that's a smaller domain because it's more computationally intense, and that's at 1.5 kilometer resolution. And the key thing is that the convective scale and the resolution is what allows us to better represent really the orographic rain that we need, that we have in New Zealand, and that's really helping kind of, you know, be in a better place to predict river floods. Hopefully that kind of makes sense. And I think Stuart has summarized nicely the terms there in the chat.
Yes, that's a good summary and a good announcement for the webinar, which will take place in 2 weeks from now. Thank you very much, Doug, and thank you very much, Stuart. We have a question from Celine. Could this geofabric and information be obtained from global data sets? Is this difficult for small islands?
Yeah,
go ahead.
Go, Celine.
No, I was just going to say some people are doing this. So I have a colleague of mine from the Netherlands that has been looking at using global information of DEM to look at models in the Pacific Island and also New Zealand. It could be that some of the resolution might be too coarse, but I think we're getting in a stage where more and more information is available, and it may be worth checking what's there to see whether it's good enough or not. Christian, if you want to add something.
No, I was going to add to say the same thing.
Excellent. Well, I'm mindful of time. If there are no other burning questions from the floor, I'd like to close this this event. Any other questions? No? Well, many thanks to the audience for joining us today, and many thanks to the presenters for a great presentation. And I'm looking forward to see you all in 2 weeks from now, when we will have Andrew Halford presenting talking on the topic that is in the domain of fisheries. Again, thank you very much, and see you next week.
Thank you.
Thank you.
Bye.
Bye.